All right.
Okay, our next speaker is Àlex Drago. And over to you.
Yeah, absolutely. Thank you very much. And thank you very much, everybody, for being here. My name is Àlex Drago. I'm a PhD student in Aalto University, all the way in Finland. And today, I'm going to present to you a work that I've done together with my professor, Jorge Núñez, that is titled Accurate Optical Tracking of Orbital Objects in Severely Trailed Images. It has applications in LEO satellites, especially for mega constellations. It has applications in extremely faint objects, like CubeSats, for example, and also for space debris. So, to give you a little bit of an overview of what we have in front of us and what we want to do, first of all, we want to optically recognize the stars from astronomical images, and especially when we are doing tracking of satellites. So when we are following it with our camera or our telescope. And a good example of this is this image that we have right here. We want to do so with high precision for the calibration or the astronomical reduction. And then we want to avoid multiple recognitions of objects in one single trial. A good example of this is this thing that we see right here, that the software is recognizing more than one object in that one single trial. So, the aim of this project is to optically recognize and track satellites from severely trailed images using actually a free and easy access software for easy implementations for professional and amateur astronomy. So, consider the following, that you have a telescope or a camera and you are tracking your satellite. While doing so, the stars in the background are going to do the following. As we are moving the telescope, we are creating a trail created by this star, because in theory, they are apparently static in the sky. So, what we want from our software is to generate a geometrical center from two positions, x and y, and after that, we want to generate two lines from the minimum and maximum distance of the boundary of this trail. In other words, what we are generating is a semi-minor and a semi-major axis. With that, this is going to define the output parameters of our software, and we're going to use them to actually position an ellipse with this data. So at the end of this, after using our software, we're going to have the geometrical center of this trail as well as an adjusted ellipse using the geometry of this trail. So the software that we're using, I'm sure that most of you are very familiar with it, is the source extractor. That is free, easy access. You can use it in any types of operating systems. And it's basically a neural network that recognizes objects in fixed astronomical images. What we are going to do is going to play with the input parameters. And for the sake of this presentation, we are going to focus on three of them. The first one is the blend mean count. And if you remember before in my first slide, we were talking that we had objects that we were mixing with each other. And in one single trail, we have a recognition of more than one object. Thanks to this parameter, what we can do is actually blend two ellipses that are close to each other. Or in other words, that they have similar orientation and actually geometrical center. On the other hand, we are going to focus as well in this variable that is called detect mean area. And this variable actually makes the condition of a minimum of pixels above a certain threshold for the object to be recognized. And then finally, the threshold, the detect threshold, that is going to set that threshold of brightness. So all the data that we're going to show here, it was gathered thanks to the telescope Fabra-Roa-Montsec, TFRM, in other words. And basically, we have used, the Baker Nunn camera and a refurbished version of it, or renewed, in other words. The previous one, before the refurbishment, it had a very large field of view, as we can see here in these specifications. And basically, let's focus on the campo visual, or field of view in English, that was very, very big, 5 degrees per 30 degrees. The new version, the refurbished version that we're using for our images, it has a smaller one, but not small at all, of 4.41 times 4.41 degrees. So a good example of what I mean by that is, for example, the M31 Galaxy. This image was taken during 70 seconds, and what you can see, the field of view is pretty big. So if we get into the results, first of all, we try to characterize our adaptation for geosatellites. In this case, we have an Hispasat, a geosatellite, of course, and we left the recording of, or the image, the time exposure of this image for around 10 seconds. This generated very small trails, but the satellite was very bright and the stars were very bright as well. So the adaptation was pretty easy in this case. We can even see here in this part right here some object that we don't know very well what it is. Maybe it was a satellite, maybe it was even a piece of space debris. However, when we come closer to the Earth, the satellites move much faster. In this case, the strategy that we used originally to get this image was to make a shorter time exposure. When this happens, the satellite is dimmer, the stars are dimmer, and it complicates in general astrometrical reduction. And not only for this, but for all the people here that is using optical astronomy. So in this case, we had to reduce a lot the threshold for brightness, and it complicated overall the detection of these stars. However, what we propose is to use longer timescales, and the image would look similarly to how a LEO image looks. Let's take a look. So in this case, we're using a SMOS, which is a LEO satellite that obviously, when it goes through the sky, goes very, very fast. If we want to detect it, even if we leave around 2 to 3 seconds, it's going to leave very, very, very long trails. So what we propose, and the strategy that we have proposed to actually be able to do the astrometrical reduction of these images, is to do 2 runs. One that is going to detect the star field, and another one that is going to detect the satellite. The strategy is a little bit doing long minimum pixels above a certain threshold for a low threshold to actually detect all this star field, and then do the exact contrary to detect the satellite. So, all of this sounded very pretty, but what is the application of all of this, right? So, the first example that we can see is that we were able to detect this CubeSat that is in a MEO orbit. Obviously, if we want to see a CubeSat, we need exposure times that are high enough to actually get all these photons from the satellite. So the trails that we have here are very, very long, and we have a very faint object, but it's detected anyway. The good thing of this is that we were actually able to do the astrometrical reduction of this image right here. Right now, I'm showing you a table of different measurements done with CubeSat. And the first thing that we have to see here is that we have a magnitude that is very high, or in other words, that is the object very, very dim. One important thing of this is that the accuracy is very, very high. That was actually our objective at the beginning of this presentation. Despite we had high accuracy, despite we have very long trails with pixels that are around 400 of them. But there are more applications. And for example, with the problem that is gathering us right here all together today of the mega constellations. So when we want to do this optical observation of these LEO satellites, we are able to leave our camera following that satellite for a long time. And a good example of this is this image of the OneWeb, that the OneWeb is right here, and then the same image of a Starlink, where you cannot appreciate very well, but also is detected the Starlink right there. So, just as a little example of what we've done, we have been able to measure the magnitude over a certain span of time with one pass of, in this case, OneWeb 0165 in the night sky. So, quickly as a conclusion, I wanted to say that we have successfully adapted the software of source extractor that is free and easy access, and what I mean by that is that you can use it in absolutely any operating system to optically track satellites in all kinds of orbits. It does it with very high precision, and it has very high accuracy as well. What it means is that we can actually use it for many, many applications. These applications that we are advancing is, for example, for the optical detection of extremely faint objects. An example is CubeSat, but we have many examples of small satellites that are very faint in the night sky. We can actually do the total contrary. We can actually study mega constellations, for example, that are so bright and cause so big of a problem. And then, finally, which was the main motivation for this project at the beginning, it was to track space debris. The good thing about all of this is that now we are also enabling people that doesn't have the resources to buy a very expensive software to actually use these things for astronomy as well. And well, this is all. Thank you very much. Here is my email if you have any questions or inquiries. And yeah, this is all. Thank you.
So thank you. We have time for a few questions, if we have any in the house or online.
Thank you. My name is Ovidiu Vadovescu from ING La Palma. So, observing asteroids, near-Earth asteroids. So, to understand correctly, are you freezing the satellite by tracking it once,
Yes.
and then take another image at sidereal rate to solve the stellar field, right? Astrometry.
We get the image after tracking the satellite, and yes, what we are doing is doing the reduction using actually this software. Yeah. Thank you.
Any more? No? Thank you again.
Thanks to you.